thanks for watching. And in the previous video, I used Green's theorem to find the area of any polygon. Here in this video, I will use the divergence theorem to find the volume of any polyhedron. Polyhedron, think of it as a pyramid or a soccer ball, anything where like the faces are polygons. And unfortunately, it's too complicated to do in full generality, but what I'll show you is, first of all, I will give you a very general formula. It's, in theory, it's useful, but in applications, it's not. And then I'll do more and more specific examples until I get a very concrete formula for a very general, very specific polyhedron. So, part one, let's do it in full generality. Full generality. Suppose you have this polyhedron, let's call it E. Well, first of all, we know that the volume of any object is the triple integral of 1. But 1, you can also think of it as the triple integral of the divergence of f, where f is 1/3 xyz. So, in other words, what is the divergence? You take the sum of the derivatives of each component. So the x derivative of x is 1, the y derivative of the second component is 1, the z derivative of the third component is 1. So you get 1 plus 1 plus 1 over 3, which is 1. So 1 is indeed the divergence of f. And then there's this beautiful theorem called the Divergence Theorem, which tells you that the triple integral of the divergence is the double integral over the surface of the surface of E of f dotted with n. Where n, what is this? It's just the outward unit. No, sorry. Well, it depends what you mean, but f dotted with n ds, where n is the outward pointing unit normal vector to the surface. It's a vector of length 1, which is sort of perpendicular to the surface. And the important thing to notice here, if you have a polyhedron, then the surface is just made up of a bunch of faces. Let's call each face fi. And therefore, what this becomes is just the sum over I of this integral over the face fi of f dotted with n. But what is f? Is just, really, the vector x has just x, y, z as its component. So it's 1/3 times x. And therefore, in the end, we get that the volume of your polyhedron so volume of E equals the sum over all the faces, I, 1/3 times the double integral over the face I of x dotted with n ds. And of course, x depends on the face, n depends on the face. Okay, now let's calculate that more precisely. So suppose you have the face, fi. Because it's a polyhedron, it means that the face is a polygon, which is a coplanar. So it's included in a plane. And suppose the equation of that plane, so suppose this is a point x naught, y naught, z naught. Suppose it's included in a plane of the form a x minus x naught plus b y minus y naught plus c z minus z naught equals to 0. And bear with me, it'll make sense in a second. Now, the nice thing is, if you have an equation of a plane, it's very easy to produce a normal vector. It's just ABC. So the normal vector in this case is just ABC, and assume it's like outward pointing. And to get really a vector of length 1, you have to divide by its length. So it's square root of a squared plus b squared plus c squared. And the point is, so this is a super general formula, but in our case, this will simplify. And again, yes, it's very abstract and difficult, but we're also doing a very difficult problem. So now, then x dotted with n. And again, x is just x, y, z. And n is this ABC over square root of a squared plus b squared plus c squared. And then that just becomes, again, this factor 1 over square root of a squared plus b squared plus c squared times, so a times x plus b times y plus c times z. So ax plus by plus cz. Now it would be nice if we can rewrite this without x, y, and z. Because if this is constant, we can pull it out of the integral and get something easier. But it turns out we can, because we have this equation. Let's expand it out. Ax minus ax naught plus by minus by naught plus cz minus cz naught equals to 0. And we get ax plus by plus cz equals to ax naught plus by naught plus cz naught. So this thing just becomes 1 over square root of a squared plus b squared plus c squared. Just literally you replace x, y, and z with naughts. So ax naught plus by naught plus cz naught. Which is way better, because again, this doesn't really depend. It doesn't depend on x, y, and z. It just depends on the face. Where again, x naught, y naught, z naught is just one point on the face. So you just need one of them. So then the double integral of fi x dotted with n ds becomes the double integral of this constant over ds. But the point is, this is constant with respect to the face, so it drops out. 1 over square root of a squared plus b squared plus c squared times, again, ax naught plus bx naught plus cz naught times double integral of 1 over the face. But the double integral of 1 over any surface is just the area of that surface. So area of fi and we can just rewrite this a little bit more. So, and then I'll summarize. Because ideally we like to write this without a, b, and c. So this really becomes 1 over square root of a squared plus b squared plus c squared times, ABC dotted with x naught, y naught, z naught times the area of fi. And again, what is this? It's just a unit normal vector to the surface. So it becomes xn dotted with x naught times the area of fi, where the vector x naught is just x naught, y naught, z naught. So what do we get? We finally get our super general formula So the volume of a polyhedron, it's 1/3 times the sum over the faces Fi of x naught dotted with n times the area of Fi. Okay, and what is x naught? It depends on I, so it's just a random point on Fi, and n is just a unit normal vector to Fi. And this unit normal vector doesn't depend on the point at all because Fi is just included in the plane. So the picture is as follows. So again, we have a polyhedron. And suppose this is a face Fi. To find a volume, for each face, you pick a random point, x naught, and you find a unit normal vector, n, and you just dot x naught with n, and you multiply it by the area of Fi. And very important, make sure that the n points outwards. Lastly, it could be that with the choice of n, this is negative. So to actually get the actual volume, you put absolute values. Just a technicality. If at the end your answer is negative 2 pi, you made a, there's some business with the orientation going on that gives you a negative answer. So in the end, put absolute values. Okay, I know this is complicated, so we got, for general polyhedra, we get this very complicated formula that's not very useful at all. It would be nicer to actually have a concrete formula for the area and a concrete formula for the unit normal vector. In general, there's no hope, because if you just have if Fi is a complicated polygon or something, it's hard to find the area. But in some cases, it's easier, namely in the case where the face is, let's say, a parallelogram or a triangle. So, part 2. So, if, let's say, Fi is a triangle, and similarly for the parallelogram, or I'm not going to write that word down, but a parallelogram, then it turns out there's a much nicer simplification to this. And let me tell you how to get it. Suppose you have a triangle with 3 vertices. Let's say A, B, C. Then, turns out that triangle can be described with 2 vectors, u and v. So u is just the vector AB, and v is the vector AC. And there are a couple of nice things about it. First of all, given vectors u and v, it's easy to find a vector perpendicular to both of them, namely u cross v. That's why it's so important, the cross product is so important. It gives you 2 vectors perpendicular. It gives you a vector perpendicular to 2 other vectors. And by the way, I made a joke up last week. It's not too funny apparently, but why did u cross the road? To get a vector perpendicular to itself and the road. Okay, anyway, so the point is u cross v becomes a vector perpendicular to the triangle, and therefore to get the unit normal vector, you get u cross v divided by the length. Right? It's always the vector divided by its length, and depending on the orientation, you get a plus or a minus sign. That's the first thing. Second of all, how do you get the area of the triangle? Well, it's half times the area of the parallelogram, which becomes half times the length of u cross v. So area of f, I guess, or fi or something, equals to 1/2 times the length of u cross v. And for the parallelogram, it's the same, except without the 1/2. Good. So now, what happens to this formula? It becomes much, much easier. So let's actually apply this now. So the volume equals to 1/2 over the sum of the faces Fi. Okay. And so we need a random point on the triangle. So this point, the point A, let's just call it vector A. So it just becomes one vertex of the triangle. It doesn't matter if you use A, B, or C, dotted with the unit normal vector plus or minus u cross v over length of u cross v times the area of the face, which just becomes 1/2 times the length of u cross v. This cancels out, and remember, in the end, put absolute value. And therefore, we get 1/3 times 1/2, so it's 1/6. So it becomes 1/6 times the sum over all faces Fi of plus or minus A dotted with u cross v. Okay, absolute values. Okay, and again, let me redraw my triangle. I don't know why I erased this, but we have A, which is represented by the vector A, B, which is represented by the vector B, C, which is represented by a vector C, and then what is U? It's just B minus A. So it's 1/6 times the sum of the faces plus or minus A dotted with U, which is B minus A, cross C minus A. And there's a reason I'm doing that. It'll simplify a little bit, because what is, first of all, the cross product is a determinant, but with ijk's in the first row. And it turns out if you dot it, you just get the whole determinant. So what you get is absolute value of 1/6 over, again, the sum of the faces, plus or minus the determinant of the matrix whose rows are A, B minus A, and C minus A. And here's a cool thing. Remember, row reduction most of the time doesn't affect the determinant. In particular, what I mean is, if you add A to every row, then the determinant is the same. So, and by the way, this I mean the determinant of the matrix with rows A, B minus A, and C minus A. So add A here, add A here, add A here, and you get 1/6 times the sum of the faces of plus or minus A, B, C. So this is really neat. In other words, if your polyhedron is, if a polyhedron has just vertices, if the faces of your polyhedron are triangles with vertices A, B, and C, and again, think more triangles everywhere, then the volume of your polyhedron is 1/6 times the sum of all your faces of the determinant formed by A, B, and C, plus or minus depending on the orientation. So if A, B, and C are so that the normal vector is pointed outwards, then it's plus. If A, B, and C are such that the unit normal points inwards, then it's minus. And the question is, how do you determine that? Well, with what's called the right-hand rule. So I hate it because I'm left-handed, but we have to use it. Namely, if, for example, you put A and C here, and your thumb points upwards, then the normal vector points outwards. Else, if it points downwards, then it points downwards and you have a minus sign. Okay, so here what I mean is like you put your hand on A, and then your second thing should be on B, your third thing should be on C. So in this case, the thumb points downwards and would be minus. But in other cases, it points upwards. Okay, now you might still be angry because true, it is a better formula than before, more concrete, but it's still not super concrete. It's still like hard to compute, right? Especially since at every point we have to figure out the orientation. Now let me do an even more specific case for which fortunately we have a better formula. So, and this is the case of a tetrahedron. So now we'll have a very concrete formula for the volume of a tetrahedron. So part 3. Volume of a tetrahedron. Suppose you have a tetrahedron with 4 vertices. Okay, let's call them A, B, C, and D. By this previous formula, we just need to take 1/6 times the sum over all possible vertices, more or less. So, what is the volume here? Volume equals 2. So, let's start with the first phase. So, this one, dBA, yeah. So, we want to find the, we want to sum it up, but we want to sum it up in the way that the normal vectors point outwards. So in other words, we want to find some combination such that if you take the determinant, it faces in the correct direction. Sorry. You want to find some combination of D, A, and B such that the normal vector points outwards, because then we don't have to put minuses anymore. One idea is to put your hand on D and then do B and A. So let me see. I knew I would have trouble with this. So D, okay, your index finger puts at B, your middle finger points at A, and lo and behold, your thumb points outwards. So that's why your first thing should be D, your second thing should be B, and your third thing should be A. So 1/6 times plus dBA. Like an absolute value in the end, but we'll see it doesn't matter. Now, let's move on to the second phase. Again, find some sort of a combination such that the unit normal points outwards. For example, here, put your wrist on D, your index finger on A, your middle finger on C, and lo and behold, your thumb points outwards. So in fact, DAC and then plus. Now let's deal with the third phase. For example, what you can do, I think, let me see. Yeah, you see, now you want the normal vector to point downwards because you want it to be outwards. And so one way of doing this, put your hand on A, then B and C, and lo and behold, my thumb points at you. So that works. So A, in fact, ABC. It's as easy as ABC. And lastly, what you want? You want the fourth phase, which is down below. And let's see how we can have a thumb that points down below. So we want, maybe let's start at B. Yeah, so B, D, C, and then your thumb points down below. So it's good. So B, D, C. And of course you might say, this is so annoying. I don't want my hand to hurt. Turns out we'll find a method, we'll find a formula that's even easier. But let's just write down, let's just rewrite this a little bit into something that's easier to handle. Okay, so this turns out, it becomes, so, and again, remember the absolute value. So DBC, if you flip the two rows, then you get BDC, if you flip the two rows, you get minus DBC. No, let's leave it like that. Okay. Now that's one way of doing it. It turns out there's an easier formula, and let me tell you. So, I'm cheating a little bit because I first find a formula and then I just show you it's actually the same thing as before. So suppose you have this tetrahedron and calculate the following. So, AB cross AC dotted with AD. So notice. AD dotted with AB cross AC. What is that? That's in terms of what points? D minus A dotted with B minus A cross C minus A. And that's D minus A dotted with. So B cross C minus B cross A minus A cross C plus A cross A, but A cross A is just 0. And then dot that, so D dotted with B cross C minus D dotted with B cross A minus D dotted with A cross C minus A dotted with B cross C. And the other one, A dotted with B cross A, well, A is perpendicular to B cross A, so the dot product is 0. And A dotted with A cross C is 0. So, because A is perpendicular to A cross C. And lastly, let's write that down in terms of determinants. So that's DBC minus DBA minus DAC minus ABC. And well, we almost have the same thing as before. Notice we have DAC, we have ABC, we have DBC. Sorry, no, we don't have DBC. We have DBC, which is minus that, and then DBA. And lastly, all we need to do, write DBC in terms of BDC. But you're just flipping the two rows. That's where we get minus BDC. So in particular, if you take the absolute value of this, so if you want to be, without using the formula, you do this, you write that in terms of dot products, and you write that in terms of this, where you add some terms that cancel out, and then you write it in terms of this, and in terms of this. So what this becomes is that absolute value of AD dotted with AB cross AC, that's absolute value of all other things, so minus BBC, minus DBA, minus DAC, minus ABC. And because we get absolute value, we get this equals to the absolute value of that. But then the absolute value of this, so the volume is 1/6 of that, so this is 6 times the volume of E, and therefore the volume of E is 1/6 times this. So I just want to show you, using our very general formula for volumes, it just simplifies to that formula. So our general formula does work, even though, again, it's super impractical. But volume of E is 1/6 times AD dotted with AB cross AC. Okay. And in general, well, you gotta watch out for the absolute value depending on the orientation. But essentially, if you have a minus sign, then you put a plus sign. And so from now, what did we do? We had this super abstract formula in terms of faces. If the faces are triangles or parallelograms, then it simplifies a bit further. And especially if you have a tetrahedron, it simplifies even further. And lastly, let me do an example. Suppose you have this tetrahedron. So let's say 2, 1, minus 1, minus 1, 1, 0, 1, 0, 2, and then 1, 0, 1. And fortunately, since I have this like on my paper like that, let me change the order of points. So this is A, B, C, that's right, D and C. And so now let's just calculate AB. That becomes minus 3, 0, 1. So this thing is minus 3, 0, 1. And AC, it's minus 1, minus 1, 2. And if you cross them, so AB cross with AC, let's see. That's determinant of IJK of minus 3, 0, 1, minus 1, minus 1, 2. If you calculate that, you get 1. So this minus 6 plus 1, which is minus 5, but with a minus it becomes plus 5, and then 3. 1, 5, 3. Lastly, AD, that equals to, I think, minus 1, minus 1, 3. So AD dotted with AB cross AC. That's minus 1, minus 1, 3, dotted with 1, 5, 3. And that's minus 1, minus 5 plus 9, and that's 3. So it is positive, and it sort of makes sense in terms of orientation, because what is ABC? So again, if you put your thumb at A here and at C here, sorry, if you put your hand with the index finger at B and then middle finger at C, my hand is hurting, then your thumb points this way. So in fact, here, the unit normal vector points this way. It should point the other way in general. So technically you have to put minus. But AD also points this direction, turns out. And therefore the dot product is positive, which makes sense. And therefore the volume is absolute value of 1/6 times that. So AD dotted with AB cross AC. And that's 1/6 times 3. And that's 1/2. Again, absolute values, absolute values, absolute values. And that's 1/2. So in the end, the volume of this tetrahedron is 1/2. And shouldn't be also surprising that you get a determinant in this case, because it basically becomes, I think, 1/6 of the volume of a parallel pipette. The volume of a parallel pipette is given by the determinant of the 3 vectors. Whew, I know. Very difficult, but I think also very exciting. So if you stuck around, congratulations. I'm very proud of you. And or you just fast forwarded. I don't know if you did that. And if you like that and you want to see more math, please make sure to subscribe to my channel. Thank you very much.